Fourier series part 2. So Fourier series, the equation would be integration from 0 to t0 of the magnitude of ft, or the signal that is given to you, times dt, which is less than infinity. So a0, an and bn must be finite. So a0 would be the dc component, an would be the cosine component, and bn would be the sine component. So the t should be convergence. So convergence for all t, ft should be less than infinity. Right, the convergence of the Fourier series can be determined by using the Dirichlet condition. So what does it mean by this condition? The function ft should be absolutely integrable, where it should satisfy the Fourier series equation that we have seen before, where it should be less than infinity, meaning that it must have only a finite number of finite discontinuities in one period, and the function ft should contain only a finite number of the maximum and minimum in the given period. Let us see how the convergence of the Fourier series happens, okay, as the harmonic increases. So here is the Fourier series with 5 harmonics. So what happens if you increase the amount of harmonic? It will become more smooth. So this is 10 harmonics. And this one is 15 harmonics. So you can see the trend goes where it will become more smooth as a perfect square wave like this. So when you have all the harmonics together, it will become a perfect square wave Fourier series signal. Now, what is Gibbs phenomenon? So when you have a sudden change of amplitude that occurs in a signal, and the attempt is made to represent it by a finite number of harmonics in a Fourier series, so the overshoot here is what we call as the Gibbs phenomenon. So when you increase the amount of harmonics, so here you have the signal, okay? So when there is an abrupt change, a sudden change at the corner of the wave, like this one here, so you have a change of amplitude from this point to this point. So the one that is in circle over here, this is called as the Gibbs phenomenon, where the overshoot at the corners happen. Now, let us see into the exponential Fourier series. So you know that there are 3 types of Fourier series. So the first one is trigonometrics, and then we have the complex trigo, and finally we have the exponential Fourier series. So Fourier series representation of a signal at t in exponential is shown here by this equation. So you have xt is equal to the summation of dn. So dn here is the harmonic function, where n is the harmonic number, times with exponential jn omega naught t. So n here is the harmonic number. So dn is equal to 1 over t naught, the integration of xt, which is the signal, times with exponent minus jn omega naught t dt. Also given here that the omega naught is equal to 2 pi over t naught, where it is the fundamental frequency. So t naught here is the fundamental period. Let us look into this example. So consider the periodic square wave at t shown in the figure. So first you have to determine the complex exponential Fourier series of the signal. B, you have to determine the trigonometric Fourier series of the signal. So the first one, you have to find out what is the complex exponential. Second one is the trigonometric Fs. So for the first one, so you have the complex exponential equation, which is xt equal to the summation of ck exponent jk omega naught t. So ck here would be your harmonic function, the dn. So times with exponent jk omega naught t. So k here is your harmonic number. And then you have omega naught is equal to 2 pi over t naught. So how do you find ck? So ck is equal to 1 over t naught, which is using this equation over here. 1 over t naught, the integration from 0 to t naught, t, okay, that is the given signal, times with exponent minus jk omega naught t dt. So this one would be equal to 1 over t naught from 0 to t naught over 2, because we are taking this square wave over here, okay, one cycle of it, times with a. So a here is the amplitude. A times exponent minus jk omega naught t dt. So now you have to solve this integration, okay, by solving all the integration here. So in the end, you will have xt is equal to a over 2. So this will be your c naught plus a over j pi. And then times with the summation of 1 over 2m plus 1. And then times with the exponential, which is exponent j 2m plus 1 omega naught t. Next, we have to solve for the trigonometric Fourier series equation. So here, you just have to transform it into trigo series. So you will have xt is equal to a over 2. So this is the DC component. So the harmonics will be 2a over pi times with the summation of 1 over 2m plus 1 sine 2m plus 1 omega naught t. So by converging that, you will have a over 2 plus 2a over pi times with sine omega naught t. So this is from this equation where your m is equal to 0. So that's why you will have sine omega naught t. And then plus 1 over 3, because your m is now equal to 1. So you have 1 over 2 times 1 plus 1, that will be 1 over 3. And then sine 2 plus 1, so sine 3 omega naught t over here. And then after that, your m is equal to 2. So plus 1 over 2 times 2. So that is 4 plus 1. That will give you 1 over 5. Sine 5. So this is because 2 times 2 plus 1. So that is 5. So sine 5 omega naught t and plus so on.